Hello everyone, welcome to the electromechanical devices. Today's lecture we're going to continue the topic that we started the previous two meetings. We started the chapter 2, which is the resistive circuit analysis, and the target is to do analysis for an electrical circuit. As we mentioned, analysis for an electrical circuit, it means that is to find any unknowns, any one of the unknowns of an given electrical circuit. And this unknowns, it would be a resistance, it would be current, it would be voltage. But in terms of analysis, since we talk about analysis, in many of the cases the resistances will be given, and your objective is just to find the unknown. It would be in the form of a current or a voltage in this case. But we mentioned in case that you would like to design an electrical circuit, it means that in many of the cases the resistance is going to be the unknown, and your objective is just to come up with the suitable resistance for a certain electrical circuit to achieve a certain performance or to achieve a specific target from electrical perspective. But basically, since we are doing analysis, so as we mentioned, the unknowns will be definitely the current and the voltage. So we're gonna continue this topic today, and we first I'm gonna go over very quick over the topic that we discussed the previous meeting. We introduced for the electrical circuit analysis, and we said that is to determine the unknown currents flowing in the circuit or unknown voltage across an electrical element. And we said that basically we do have four methods of doing analysis for electrical circuit. This would be the first method that we already discussed and covered, and we practiced, and we solved lots of examples over it, which is the Kirchhoff voltage law, Kirchhoff current law, and Ohm's law. Just to apply these three laws for any given electrical circuit, you can simply figure out and do a complete analysis for this electrical circuit. Then we had introduced the previous meeting for the series and parallel equivalence, and this is the second method that we're going to consider today with more examples and more demonstration. But and basically we introduce what is the difference between series resistances and parallel resistances, and how we can calculate the equivalence of a set of resistances that already arranged in a series way or parallel way. The third, fourth method, this will be covered in the next meetings. But for today, we're just going to consider the series and parallel equivalence methods for analysis for electrical circuit. And going ahead very quick to this topic here, we discussed that series resistances, these are the ones that are that having the same current, like any set of resistances. Like this case, this is resistance R1, R2, R3. To evaluate this resistance, whatever they are in series or parallel, the key idea that they should have the same current, or the current passing through each one of these, it should be the same. So if we decided, as we practiced before, if we decided to distribute the current, we're going to have a source which is V, and the total current will be I, which is going to keep flowing through the three electrical circuits. So simply we can combine them into an equivalent resistance, which is R equivalent. This R equivalent, it should be the sum of R1 plus R2 plus R3. Why? Because they are series, and we had proved this in the previous meeting, and we had proved this relation, why the equivalent resistance of series resistances should be the sum of all the resistances, which is R1 plus R2 plus R3 plus R4 and so on. It depends on how many resistance, but the key idea or the key point that they should have the same current. But as for the parallel resistance, as we discussed in the previous meeting, that the current should be divided among or over these parallel resistances somehow. That they, like for example, like this electrical circuit, if we decided to distribute the current, we're going to have the total current I, which shall be divided over R1, R2 into two currents, or basically it should be divided into three currents. Like if we use some I1 plus I2 plus I3, this should gonna give us the total current, which is I. So it means that the current is going to be divided over these three resistances. So what does it mean? This means definitely that these resistances, they are parallel ones. What does it mean parallel? It means that we can combine them into an equivalent resistance into this form. Like it looks like you already simplifying the given electrical circuit into an equivalent simplified form. which is the classical electrical circuit. So the equivalent, but we have to combine all of these resistances together into one equivalent resistance. This is the R equivalent. This R equivalent automatically is going to be calculated through this equation or this relation, and we had proved this one in the previous meeting, that it should be 1 over R equivalent equals the inverse of the sums, the sum of the inverses of the inverse of all of these resistance all together, like 1 over R1 plus 1 over R2 plus 1 over R3 and so on. How it depends on how many resistance that we have. We said that this equation or this relation for the R equivalent for better resistances, in case that you just has two resistance, this is just only for two resistances, we can say that directly that R equivalent is going to be the R1 plus R2 R1 times R2 divided by R1, their sum, which is R1 plus R2. And we said that this one is, it can be derived from the general form, but this is like a very quick, if you just did the multiplication and the sum to end up with the R equivalent, because here it is the inverse, you're going to end up with this relation as we discussed the previous meeting. There is a very important note that we have to consider here, that the voltage across the battery resistance, it should be the same. Again, the voltage across battery resistors, it should be the same. So what does it mean? It means that if I ask you how much is the volt over R1, how much is the volt over R2, how much is the volt over R3, you should understand and realize that R1, the voltage over R1, R2, R3 should be the same. It should be equal. Why? Because they are battery resistant. This is one of the characteristics and the properties of the battery resistors. So again, for battery resistor, the voltage over all the battery resistors should be the same. So if I ask you how much is VR1 or the volt over R1, it should be V. Why? This is like this branch is better to this branch. So the volt between these 2 points, it should be equal to the volt between these 2 points as well. Equal the volt between these 2 points, equal the volt between these 2 points. It means that the volt over R1, R2, R3, all of them are equals to the total voltage, which is V. You should understand a point like this one. But for the series resistance, the current over all the resistance should be the same. So it is very simple. In case that we have set of resistances, that the voltage over them is equal, is the same, it means that definitely, by definition, these resistors should be better resistors. But in case that if we do have a set of resistances or resistor that the current over them is the same, it means that these resistors definitely, by definition, they should be series resistors. Make sense? So this is what we introduced the previous meeting. So what we're gonna do today, basically, we're gonna consider, first I'm gonna start with some example like these examples, how we can calculate the equivalent resistance. Then we're gonna discuss two new topics, which are the voltage division principle and the current division principle, and know how we can use them for doing analysis for resistive circuits. Using the equivalent method, the equivalent resistance method, and we're gonna consider examples. The rest of the lecture is gonna be just more demonstration by solving these examples. So let us go ahead and start with these examples here. So the topic of today is resistive circuit analysis, and the method that we're gonna use, as we mentioned, it is the equivalent resistance method. So as we mentioned, we are discussing these 4 methods. We have covered this one, and we're still working on the second method. But as for the third and the fourth, this is what will be considered in the next meetings. Make sense? And this is the general expression for the series resistances, and this is the general expression for the parallel resistances. But we said that just for the special case that we do have 2 resistances, their R equivalent, it should be their multiplication divided by their sum. So these are the main expressions that we gonna use, and you should understand in the meanwhile that the voltage across parallel resistors, it should be the same as we mentioned, but the current over the series resistor, it should be the same. So let us consider this example here. Like we do have this electrical circuit here. Now we are not interested in the voltage or the current. We're just interested through these examples is just to know how we can calculate the equivalent resistance. So again, what is the equivalent resistance? We're already given this electrical circuit that has 1, 2, 3, 4 resistances. How about if we would like to simplify this electrical resistance circuit into a very simplified form? The simplest form of an electrical circuit, it should have the source, which is V, there should be a current, and there should be R equivalent, which should be the equivalent resistance of all of these 4 or 5 resistances. So the key idea here, and this is what we just gonna focus on for now, just how we can calculate R equivalent, for how we can combine all of these resistance into just one equivalent resistance. This is the key idea. So we should consider whatever this resistance is, it parallel, or these resistors are parallel or series, and we can apply one of these load that we discussed before. So, but the key idea that you have to stick to almost to the same procedure that we discussed in the previous meetings for doing electrical circuit analysis. The first step, in a way, you should distribute the current through the electrical circuit. So if we decided to start here, so this should be the source, there should be some source here, right? Forget about the source for now. It means that there should be current I, which is the total current that comes from the source. This current is gonna flow here through the resistance R1. So if I ask you how much is the current over R1, you should understand that it is the total current, which is I. And then at this node, at node number 1, this is node 1. At node 1, this current, it should be divided, right? So you're gonna have, this is the total current, which it should be divided into 2 parts here. So we're gonna have here one current like I1, and there is another current which is I2. It should be divided into I1 and I2. It means that how much of the current over R2, it should be I1. How much of the current over R3, it should be I2. How much of the current over R4, it should be I2 as well. Agree? This is basically what we discussed, and we practiced this a lot in the previous meetings. So if I ask you, how many resistances, or which resistances in all of these 4 resistors that they do have the same current, that you are pretty sure that in this configuration, in this distribution of the resistance, that they do have the same current. So definitely, as you're gonna look at it, so you're gonna find that R3, R4, they do have the same current, right? So what does it mean according to the definition of the resistance, whatever they are, the resistors, whatever they are, parallel or series, you're gonna realize that R3 and R4, they should be series resistors. Why they are series? Because they do have the same current. So what does it mean? It means that that is fine if we decided to combine both of them into an equivalent resistance, but let us give it a name like R equivalent 1, because definitely we're going to have more equivalents. This R equivalent, according to the definition of the series resistor, should bear their sum of the resistors. So it should be the it should be the sum of R3 plus R4. Okay? Like you're just going to sum these 2 resistors. How much is R3? It should be 5. How much is R4? It should be 15. So if we sum, we're gonna end up with R equivalent should be the 20 ohms. Make sense? So now we already have here R3, R4, they are series, and we combine them together. Make sense? So, and if we decided to redraw again the electrical circuit, after this simplification, we combined 2 resistors together into just one resistor, which with an equivalent resistance, which is 20. So we already simplifying the electrical circuit into a more simple form. So we're gonna have here, if you're gonna continue, we're gonna have R1 still be the same, and we're gonna have R2. But the only difference that we combine the R3 and R4 into an equivalent resistor, which is with 20, that as we calculated, why 20? We sum them because they are series resistors. So now let us do analysis again for this electrical circuit. Let us start from the beginning. So the first step again is just to distribute the current. If we decided to distribute the current, we're gonna have the total current that comes from the source as I, and this current at node 1, it should be divided, right? This is the total current, which should be divided into 2 currents as shown here, like I1 and I2. Make sense? So if I ask you how much is I1, I'm sorry, how much is the resistance and the current over R2, it should be I1. The resistance over R equivalent, it should be I2. Agree? So if I ask you what is the type of these two resistors together, are they parallel or series? Definitely they should be parallel. Why parallel? Because if you, as you can see, the current has been divided, has been split over two resistors. So it means that these two resistors, definitely they should be parallel resistors. So what does it mean? It means that that is fine if we decided to combine both of them, but we have to apply the relation between two parallel resistors. So these two resistors, they should be parallel resistors. So for parallel resistors, definitely, or because they are parallel in a way, resistors. So what does it mean? It means that it's fine to combine both of them into R equivalent, and let us give it a name like R equivalent 2. R equivalent 2, it should be their multiplication, which is R2 times R equivalent 1, divided by their sum, which it should R2 plus R equivalent 1. Make sense? So which should give us, if we did the calculation, this is gonna give us how much? How much is R2? R2 is 20 times R equivalent 1, which is also 20, divided by 20 plus 20. This is gonna give us, if we did the calculation, this is gonna give us the R equivalent 2, which should be 10 ohms. So this is gonna give us the 10 ohms. Make sense? So simply we can do more simplification to the electrical circuit. So we're gonna carry on the R1 as it is, but we just combine these two into just one equivalent resistance, which is R equivalent 2. So if we did so, we're gonna end up with more simplified form. So this is more simplification from here to there into R1 and R equivalent 2 with 10 ohms and 10 ohms. Now we're gonna have, if we decided to distribute the current, so we're gonna have the total current, which is I. This total current is gonna keep roaming and rotating into the whole electrical circuit. So if I ask you how much is the current over R1, it should be the total I. How much is the current over R2, R equivalent 2, it should be the total current, which is I as well. So what does it mean? It means that these two resistors are series resistors. So that is fine if we decided to combine them. These are series. So that is fine to combine them into just one R equivalent. And if we did this, if we combine them, it means that we already, this is going to be the simplest form of the electrical circuit. If we compare R1 with R equivalent 2, we're going to end up with the simplest form of the electrical circuit. It means there is no more simplification for this electrical circuit. So that it means that this is the equivalent or the overall equivalent resistance to this electrical circuit, which should be the sum of R1, the sum of the R1 plus the R equivalent 2. Why their sum? Because they are series. So it should be 10 plus the 10, which is going to be the 220. Their sum is going to be 20, which is 20 ohms. This should be the R equivalent. So it means that if we did more simplification, we're going to end up, this is the simplest form of the electrical circuit that is going to have the total current as I, which is passing through this electrical circuit or this resistance I. So this is the total current and this is the R equivalent for this electrical circuit. So this is how it works. Like it is like too many steps basically. You have to distribute the current, and based on the current distribution, you should figure out which resistors that should be in series, which resistors that should be in parallel. And it is better to start from the farthest point, from the end of the electrical circuit, and do the simplification as you move. Because basically this is going to be the source, right? And you are going to distribute the current through the electrical circuit into I, then I1 and I2, and I2 is going to be the same. So start from the last element, the first element, the element that is far from the source, the electrical source, and then do the simplification step by step till you're going to end up with the total equivalent resistance for this electrical circuit. Make sense? So this is for the example 1. Let us consider another example, which is example 2. We do have here how many resistance? We do have 1, 2, 3, 4. And we would like to combine all of them into just one electrical resistor. or electrical resistance. So how much is the equivalent resistance? This is the key idea, and this is what we are seeking for this problem. So the process again start that we have to do simplification for this one. We have to start with the electrical current distribution. So this is going to be the total current that comes from the source. So if I ask you how much is the current over R1, it should be the total current, and then this total current is going to keep going. At node 1 is going to be divided into two currents as shown here. One current is going to be like I1, and the second one, let us assume that this is I2. As we discussed before many times, there is no restrictions or constraint over the which one it should be I1, which one it should be I2. It doesn't matter. Any I1, any I2. I can give this I2, this I1, it doesn't matter. So if I ask you how much is the current over R2, it should be I1. How much is the current over R3? We don't know yet. Why? Because we have to do more division. We have to divide the current more. Because if this I2 is going to keep going, it's going to be further divided into I3 and I4 at node number 2. Agree? So what does it mean? It means that if you summed according to the Kirchhoff current law that we discussed before, and if you summed I3 plus I4, this should give us the total current, which is I2, but the sum of I2 plus I1, this is going to give us the total source current, which is just I. So if I ask you how much is the current over R4, it should be I4. How much is the current over R3, it should be I3. Make sense? So if we start from R4, the first resistance from the source, this should be the source here. The source, the better it should be here. So what we're going to do, we're going to start from this resistance. What is the relation of this resistance to this one? Is it parallel to it, or is it in series with it? So definitely it should be in parallel. Both are in parallel. Why? Because the current, the total current, which is I2, it's going to be divided into I3 and I4 over these two resistors. It means that these two resistors are parallel resistors. So it means that if we decided to combine them, into an equivalent resistance, their equivalent resistance should be their multiplication divided by their sum. Why? Because they are parallel. So these two, they are parallel resistors. So simply we can do simplification to this electrical circuit. Is going to be further simplified into this form. So what I'm going to do, I'm just going to carry on the first electrical resistance, which is R1 as it is. Then we're going to have here R2. It should be the same. I won't going to do anything to these two resistors. Then what I've did here, I just combined the R3, and R4 into R equivalent 1. And how much is R equivalent 1? It should be their multiplication divided by their sum. So it's going to be the R3 divided times R4 divided by R3 plus R4. How much is R3? It should be 3 times 2 divided by 3 plus 2, which is going to give us 6 over 5. This is going to give us the equivalent ohms. This is the equivalent R equivalent 1. Like what I've did here, I just combined R3 and R4 into equivalent resistance. So I have simplified this electrical circuit further. Then we're gonna repeat again, just do again analysis to this electrical circuit, starting from this current, the total current I. At this node, which is gonna be node 1, the current it should be split and divided into, the total current it should be divided here into I1 and I2. So we're gonna have here like I1, and this is gonna be I2. So if I ask you what is the relation between R equivalent 1, which we just calculated by 6 over 5, to the R2, both of them are parallel resistors. Why they are parallel resistors? Because the current has been divided and split over them. So they should be, these two, they should be parallel resistors. Agree? So what does it mean? It means that I can do further simplification, more simplification to this electrical circuit by combining these two resistors together. So if we did it, basically we're going to end up with this electrical circuit. We're just going to carry on the R1 as it is, but instead we just combined R2 and R equivalent 1 into R equivalent 2, another equivalent resistance, and we're going to have the total circuit is going to be simplified into just two resistances, where the R equivalent 2, it should be their multiplication, which is R2 times R equivalent 1, divided by their sum, which is R2 plus R equivalent 1. This is going to give us R2, it is already given by 6 ohms, so it should be 6. This is R2 times the 6 over 5. This should be divided by the R2, which is 6 plus 6 over 5. Then we can do the calculations for this R equivalent to how much it is. Make sense? Then if we did again, so we still have one more step of simplification. If we decided to distribute the current, so this is going to be the total current I. This total current is going to keep going through the whole electrical circuit. So what does it mean? It means that the resistance, or the current over R1 and R2, R equivalent 2, it should be the same. So what does it mean? It means that these two resistances, they should be series resistance. So what does it mean? It means that we can do simplification to this electrical circuit into the simplest form, which it should be the R equivalent. We're going to end up with just one electrical circuit that include one resistance, which it should be R equivalent. This is the total R equivalent, and this R equivalent, this total R equivalent, it can be calculated as follows. This R equivalent, it's going to be calculated as the sum of R1 and R2. So R equivalent, it should be the sum of R1 plus R equivalent 2, which it should be R equivalent R1, which already given by 2. This should be given by 2, plus R equivalent 2, which we just calculated down there. This number here. Once we do the calculation, you can substitute back here. We're going to end up with something in ohm. This is how we can calculate the equivalent resistance for this electrical circuit. Make sense? So this is another example. Again, the key idea is just to distribute the current and do the simplification. Start from the resistance that is far from the source and keep going, more simplification till the simplest form. This is going to give us the R equivalent, which should be the equivalent resistance to this, all of these resistors, all of them together. Okay? And there is an important notice or something here that I should mention actually. It is not needed, in fact, for each simplification step, it is not needed to redraw again the electrical circuit. So for example, from the beginning, I'm going to say that I do have here these two resistors, they should be parallel, so I'm going to combine them together. Then their equivalent is going to be parallel to R2. Then I'm going to calculate R equivalent 2. Then the R equivalent 2, it should be series with the R1. So I'm going to calculate the overall equivalent resistance should be the R1 plus the R equivalent 2. If you realize and you can imagine how it's going to look, how it's going to be the simplified form of the electrical circuit without redrawing it again, it is not needed to redraw the electrical circuit. That is fine. That is fine to me if you just did the calculation for how much is R equivalent 1, how much is R equivalent 2, then how much is the total R equivalent for the electrical circuit. Make sense? Let us consider another example here, for which is this one in example 3. So again, start by distributing the current. So if we start from the source it should be something here, right? So starting from the source, we're going to have the total current, which is I. At node 1, this current, it should be divided into two currents, into I1. And there is another current here, which it should be I2. Okay? Then if we're going to keep going, I1 again, it will reset back again at this node and collect it back to the source again. So there is no further distribution of the current I1. But I2 should be distributed further or divided more. Why? If we're going to keep going with I2, at node 2, this I2 is going to be divided into two other currents, into I3, and there should be I4. Make sense? Then I3, it will be collected, and I4 will be collected at this node, which will reset back again to the source. So if we're going to look to this distribution, if I ask you where is the first resistance from the source, it's going to be R4. and the next to it is directly is R3. So what, if I ask you what is the relation between R4 and R3, you're gonna realize that they are better resistors. Why they are better resistors? Because the current has been divided and split it over them. Agree? So what does it mean? It means that that is fine if I combine these two into R equivalent 1. And I'm gonna consider that these two resistors are parallel resistors. Agree? Then this R equivalent 1, again, try to imagine without redrawing the electrical circuit one more time, just to save some time. So if we combine these two resistors together, so we're gonna end up with R equivalent 1. Combining these two resistors, it means that we're already combining these two electrical currents. Like we're already combining I3 and I1 together. So the combination or the sum of I3 and I4, this should give us I2. Make sense? So what does it mean? It means that if I decided to remove these two resistors and replace them with just one resistance, this resistance should be parallel to R2. Agree? So if I did it, let us draw it here. So if I did it, I'm gonna have here, and this is should be node 1, and there should be R1 resistance, agree? And there should be R2 resistance. Then what I've did here, basically, I have combined these two into R equivalent 1. R equivalent 1. This R equivalent 1 with R2, it should be in series. Both of them are in series. Why? Because they're gonna have the same current flowing through the electrical circuit. It should be the same. So the current here, it should be this current, it should be the I1, it's gonna be still the same, and the current here, it should be the I2, and this I2 is gonna keep going here as I2. So what does it mean? It means that these two, they're gonna be series. So I'm going to combine them into another R equivalent, which is going to be R equivalent 2. But R equivalent 2 is just series. So if I ask you how much is R equivalent 1, if we just decided to do the calculation, these R3 and R4 are better. So it should be their multiplication divided by their sum. Agree? So their multiplication, this is going to give us R3, which is 6 times 3. This should be divided by the 6 plus 3. If we did the calculation, this is going to give us how much? 3 plus 6. This is going to give us just 2 ohms here. So this should be the R equivalent 1. Now, what I'm going to do, actually, I'm going to calculate R equivalent 2. R equivalent 2, it should be, they should be series. So it should be the sum of R2 plus R equivalent 1, which it means that R2 is already 8 ohms. So what I'm gonna do, I'm just gonna add 8 plus 2 ohms, which is R equivalent 1 that I just got it. This is gonna give us 10 ohms as R equivalent 2. Make sense? We got R equivalent 1 and R equivalent 2. Now, let us try to do one more simplification. If we decided to combine these two resistors, R2 and R equivalent 1, into just one resistance, this one resistance, which is R equivalent 2, it should be in parallel with R1. Why in parallel? Because the total current I here, this is the total current at this node, it's gonna be split into I1 and I2, which should be the same current over their equivalent of the R2 and R equivalent 1. So what does it mean if we decided to do further simplification to this electrical circuit here? So the electrical circuit is gonna take this form. It's gonna be the R1, and these two resistors, we just combined them into, this is gonna be R1 and this is gonna be the R equivalent 2 that we just calculated by 10. So how much is the current? The current distribution, or the current, is gonna be divided between these or over these two resistors. So we're gonna have here I1, and the current here is gonna be the I2. So what does it mean? It means that I'm going to combine these two as parallel resistors into just one R equivalent. This is the overall R equivalent. This is the big R equivalent. You can say this is the big R equivalent. It's gonna be their multiplication, which should be the R1 plus R equivalent 2 divided by their addition, which is R1 plus R equivalent 2. How much is R1? It is already given up there by 10. And so it's going to be 10. I'm sorry, this should be the multiplication. So 10 times 10 divided by 10 plus 10. So this is going to give us the 100 divided by 20, which is going to give us the R equivalent of, or the overall, this should be the overall, or the overall equivalent resistance for this electrical circuit. Make sense? Another example here for this electrical circuit, and let us try to do it without redrawing again the electrical circuit. So this is going to be the total current at this node. This total current is going to be split and divided into, let's say, I1, and we're going to have here I2. So by definition, and I2 is going to, but over here is going to be I2. Then these two currents will be collected back again to the electrical circuit. So if I ask you what is the relation between R1 and R2, you're going to realize that these two are series, right? So, and we're going to calculate for both of them. Let us use a little bit different color here. So these two resistances, both of them are series. Agree? Why? They do have the same current, and their R is going to be R equivalent 1. So if I ask you how much is R equivalent 1, you're just going to simply calculate the sum of R1 plus R2, which is going to be the 1 plus 2 ohms, which should be 3 ohms. Agree? Then, if we combine these two into just one resistance, simply just looks like we get rid of one of these two resistors, and we're just using only one. Agree? But this only one is going to be their equivalent. Make sense? Because we combine them into just one resistance. So assume or try to think of it or imagine that we get rid of this resistors and we just have this one. So if I ask you what is the relation between this, like R1, which should be R equivalent 1 here, right? And what is the relation between of R equivalent 1 to R3? Are they parallel or series? Definitely they're going to be parallel. Why? The current has been split and divided over them. Make sense? It looks like, so again, if we combine these two together, it means that it looks like we get rid of one of these two resistance with an equivalent one. Just we are using one of them, but with a different value, right? So it looks like we getting rid or removing this electrical circuit resistance. So we're going to end up with just one R, one resistor, which should be in parallel to the R3. Why it should be in parallel? Because the current has been divided over them. So what does it mean? It means that we're going to have one more R equivalent, but it's going to be R equivalent 2. This R equivalent 2, it should be the multiplication of the R equivalent 1. There should be here somehow R equivalent 1 with times R3 divided by the R3 plus the R equivalent 1. Their multiplication divided by their sum. So R equivalent 1, which we just got it by 3, plus R3, which is 3 divided by, this should be multiplication divided by 3 plus 3. So this should be 9 over 6, which is going to give us the 1.5. Make sense? So this is going to give us 1.5 ohms. Then what we've done here, basically we combine these two into R equivalent 1. We combine their equivalent with R3. So we're going to end up with R equivalent 2, which it should be the total R equivalent. So there is no more simplification for this electrical circuit. This is going to be the simplest form, and the overall equivalent resistance is just 1.5 ohms for all of these resistors. Make sense? Another example here, and this is going to be the last one for calculation of the equivalent resistance. If we consider this electrical circuit, and let us start again by distributing the current at this node, this current is going to be divided. This is the total current I. It's going to be split and divided into two currents. One current here, let us assume that this is like I2 and this is like I1. So the current over R1, it should be I1. The current over R2, it should be I2. Then these two currents will be collected again here. Both of them, they're going to be collected into the total current again. Make sense? Then at this node, this total current is gonna be split one more time into another two currents. Let's say like I1, you can use even I1 and I2, but you should keep in mind that I1 and I2 will be different than the original I1 and I2. So that's why it is better to consider different numbers. So like I1, I3, and I4. So you won't gonna mix it up with the I1 and I2, the previous ones, because if you split it into I1 and I2 again, this I1, it shouldn't be, it is not necessary to be the same value as I1 here. It would be different, and in many cases it's going to be different. So that is why it is better to use different numbers. But anyway, if I ask you, if we start from the first one here, so if you're gonna see that this total current it has been split between R1 and R2. So by definition, it means that R1 and R2, these are two parallel, and the same current, which is the total current or whatever. We do have a total current which has been divided between two other resistors, which are the R3 and R4. So what does it mean? It means that R3 and R4, they are parallel, and the R1 and R2, they are also parallel. So this, we're gonna combine these two into R equivalent 1, and then we're gonna combine these two into R equivalent 2. You can give us, for example, it doesn't matter which one is R equivalent 1, which one is R equivalent 2. So if we decided to calculate R equivalent 1, how much it should be? It should be their multiplication, R3 times R4 divided by their sum, R3 plus R4. So this is gonna give us R3, which is 75, times the 25 divided by 75 plus 25. If we did the calculation, this is gonna give us the 18.75 ohms. This is gonna be the R equivalent 1 by combining R3 with R4. Then we do have R equivalent 2, which it should be the R1 times R2 divided by the R1 plus R2. Their multiplication divided by their sum, 100 times 50 divided by 100 plus 50. This is gonna give us this value, which is gonna be 33.34 ohms. Make sense? Now we combined these two into just one resistance, and we combine these two into one resistance. Once we combine R1 and R2 into one resistance, what should be the current passing over their equivalent? It should be the total current, because again, looks like you already canceling one of these two resistances. If you cancel this resistance, for example, so the total current is gonna be the one that passed through the 50. So what does it mean? We're gonna cancel one of these two resistors, and we're gonna replace this resistor with the R equivalent 1, with the R equivalent 2, I'm sorry. Because here there's some, it's gonna be their equivalent is gonna be R equivalent 2. We're gonna do the same. If we decided to do the same, so it means that the current over R equivalent 2, it should be I, the total current. How about the current over the R equivalent 1? Simply, if you get rid of one of these two resistors, so you are gonna distribute the current, right? And we replace this one with the R equivalent 1. So the current over it is gonna keep going. This total I, it won't gonna be divided. There is nothing here. So it's gonna keep going over R equivalent 1. So what does it mean? R equivalent 1, the current over R equivalent 1, it is I. The current over R equivalent 2, it is I, the same current. So what does it mean? It means that R equivalent 1 and R equivalent 2 both are series. Make sense? So it means that at the end, we can calculate an overall equivalent resistance, which is gonna be R equivalent. This is the big R. It's gonna be the sum of R equivalent 1 plus R equivalent 2. Why we are summing both of them? Because they are in series. So the R equivalent 1, we got it by 18.75 plus the 33.34. If we did the calculation, this is gonna give us the overall the overall resistance by 52.08 ohms. Make sense? So again, how we figure it out? simply try to get rid of these two resistance and replace this one with the R equivalent one. So the current won't gonna be split or divided over nothing here, right? So it means that the current will be moving the overall current, which is I. And the same thing here, if we get rid of one of these two resistors, so the current won't gonna be split, it means that the total current will be I. So what does it mean? The R equivalent 2 and R equivalent 1, both they do have the same current, which means that they already series, so their equivalent resistance will be their sum. Make sense? Right, so the next point here is the voltage division principle. And then we're gonna discuss the current division principle. So, again, the main objective is to do analysis for electrical circuits that include resistances or resistors using the equivalent resistance method. So what we have practiced so far, basically, we have practiced how we can combine all of these resistors into just an equivalent one with an equivalent resistance. So we end up with the simplest form of the electrical circuit. So from this simplest form, we can calculate simply the current, in case that the current is the unknown thing of this electrical circuit, which is going to be the overall current or the total current of the electrical circuit. Or in case that the voltage is the unknown, we can simply find the unknown, and the current should be given in this case. Make sense? So whatever it is, the unknown, it means that we're going to end up with the simplest electrical circuit, which is going to be a one similar to this one. Like we're going to have R equivalent, this should be the total resistance, and we're going to have here a source with Vs, let's say this is the total source voltage, and there should be current here as Is, which is the total current that should be generated by this source, and this current, it should be the one that roams through the electrical circuit. So if we apply Kirchhoff voltage law to this electrical circuit, we're gonna end up that Vs intuitively is gonna be the Is times R equivalent. So we do have three parameters here. If you given two, you can simply calculate the third one. It is very simple, very easy thing. No worries. So simply, in case that we do have an electrical circuit and our main interest is just to figure out the overall current, the overall voltage, simply combine all the resistances together into R equivalent, you're going to end up directly with this simple equation to figure out the unknown, whatever it is, Is or Vs. Very simple. But how about if we do have an electrical circuit, the original one, not the simplified, this is the simplified electrical circuit for this one, for example. So for example, if our interest there is not just to calculate Is or Vs, how about if we are interested also in the current, the voltage over this resistance, or the current through one of the resistors of the original electrical circuit. So it means that we have to do further calculation or further analysis to the electrical circuit, but we have to consider the original form of the electrical circuit. But this, if we did it basically, somehow we had to use the Kirchhoff voltage law, current law, and Ohm's law which is gonna be the first method. But here we don't need to use the first method, and we have to use the equivalent resistance method. So we end up with Is and Vs. So the question is, for example, is there any way, because this is going to be the total voltage through the electrical circuit, right? And this voltage, it should be distributed over all the resistances that form the original electrical circuit, right? So is there any way to find the voltage over any resistance in relation to the overall voltage that we got, which is Vs, through this equation? So again, like this is the total voltage from the source. So the question is there any way to figure out the voltage over R1, the voltage over V2, the voltage over V3, in comparison to how much it is in case that you already given V total? Can we figure out it directly without solving Kirchhoff voltage law? We can apply Kirchhoff voltage law to this loop to calculate the volt over any one of these elements. No worries, we can do it, right? But the question is, how much is V1? or V2 or V3 in comparison to V total using the equivalent resistance. Can we figure it out? Yes, we can. In this case, we have to apply the voltage division principle. The same thing applies for the currents. How about this is the total current? And how about if we do have an electrical circuit like this one, and we're already having the total current that comes from the source? We can figure it out using this equation from the simplified electrical circuit. So the question is, how much is I1 in comparison to the total current? How much is I2 in comparison to the total current? Because this total current is going to be divided, right? It should be divided over these two resistors, right? So how much of the current that R1 is going to take in comparison to the current that R2 is going to take? It means that how much is I1 and I2 in terms of I total? Can we figure it out without applying Kirchhoff current law? Yes, we can, but we have to use the current division principle. So these two principles, basically, they had been derived based on the concept of the equivalent resistance. So that's why we are explaining or introducing these two principles in the context of the equivalent resistance method of the electrical circuit analysis. And this is what we're going to do. So simply, before I'm going to go over the definition of the voltage division, then we're going to move to the current. Let us first know how we can derive this equation, but let us demonstrate this very important notice here or point that you should understand. That the voltage division principle, it is only applicable to series resistors. So the condition is for series resistors, we have to apply the voltage division principle. Why? Because intuitively, since we are talking about series resistors, as we mentioned, they do have the same current. So there is no way for us to divide the current over them. There is no current division that can be applied to series resistors, while the current stays the same over them. But the voltage will be divided, will be distributed. The total voltage that comes from the source, this total voltage that comes from the source is going to be distributed over the three resistors. So the question is, how much is V1, how much is V2, how much is V3? Or how much of voltage that the R resistance R1 is going to take from the total volt, how much is voltage R2 is going to take from the total volt, how much is the fraction of the voltage of R3 that is going to take from the total volt. This is our interest. This is the voltage division principle. So again, the voltage division principle is applicable to series resistors only. Make sense? So how it works basically, let us assume that our main interest is just to calculate V1. So let us do a little bit calculations here. So as we agreed, we can simply combine all of these resistors, all of them together into an equivalent resistance, which is R equivalent. So if I ask you how much is R equivalent, you're gonna tell me that R equivalent, it should be their sum, which it should be the R1 plus R2 plus the R3. Why their sum? Because they are series. Again, the division principle, it should be the voltage division principle should be applied to series resistors. Make sense? And now the question is, how much is V1? How much is V2? How much is V3? Again, what is V1, V2, V3? These are the voltages over R1, R2, R3, and respectively. Like how much is the V1 over R1, how much is V2 over R2, how much is V3 over R3. So if I ask you to do it simply, if I ask you how much is V1, how much is V1 here? V1, simply it should be the total current, which is I, times R1. Make sense? From this equation, how much is the total current? Assume that this is like IS. This is the total current, which is I. So how much is I from this equation? This equation that we just got it from the simplified version of the original electrical circuit. This is the original circuit, but this is the simplified one, right? This is the simple form of the original circuit. Make sense? So if we apply Kirchhoff voltage law to this one, we're gonna say that the total current, which is I, it should be the Vs, which is the total voltage, divided by the R equivalent. How much is R equivalent that we just calculated? It is the sum of all of these resistances. Make sense? So it means that this I, it should be the Vs divided by R1 plus R2 plus R3. Agree? So if we substitute it with this form here, so how much it should be V1? So V1 intuitively, just replace I with this expression. So it's going to be Vs divided by R1 plus R2 plus R3. Agree? Times, this should be multiplied times R1. So let us replace this R1 with Vs. So which is just consider Vs as a common factor. So we're going to end up with R1 over R1 plus R2 plus R3 times Vs. So with this form here, simply, we're going to say that the fraction of the volt that R1 is going to take is going to be R1, which is the resistance itself, divided by the sum of all of the series resistors, or the series resistance. Make sense? And this what introduced the meaning or the definition, and this is the basic definition of the voltage division principle. Like instead of doing all of this calculation, we won't gonna do it anymore. We're just gonna directly calculate use this expression directly. Like for example, how much is the fraction of the voltage like R1 is gonna take from the total voltage is gonna be its resistance divided by the equivalent resistance of all of the resistors within the electrical circuit. Very simple. How much is V2? If we apply the same concept, how much is V2? V2 is going to be its resistance divided by the sum of the resistors of all the resistors within the electrical circuit. The same thing for V3. How much it is? It's going to be R3 divided by the sum of the resistances, or the R equivalent for the series resistances. Make sense? So what does it mean? It means that each one of these resistance takes voltage depending on its resistance value. As much as the resistance of the electrical circuit increases, the voltage over this resistance, it should be bigger or increase. Why? It has direct relation to the voltage. And this what defines the voltage division principle. Like simply, if you would like to calculate V1, it's going to be R1 over the sum of all of the resistance within the electrical circuit. And this is only applicable to series resistors. So of the total voltage, this is the statement of the principle of the voltage division principle that states that of the total voltage, the fraction that appears across, or the fraction of the voltage across a given resistance in a series circuit, is the ratio of the resistance to the equivalent resistance, or the equivalent one. Make sense? This is the statement of the voltage division principle and how it works. And simply we can use it, and we're gonna use it when we do analysis for electrical circuits using the equivalent resistance method. Make sense? Let us move to the current division principle. So the current division principle, as mentioned here, and this is very important, notice that you have to consider that the current division principle is applicable only to parallel resistors. But the voltage division principle is applicable only to series resistors. This is the difference. So if we do have some parallel resistors like these two resistors in this way. So R1 and R2, they are parallel. Why? The current has been divided over them. So the question is, how much is I1 in terms of I total? How much is I2 in terms of I total? Or in other words, how much of current does R1 take from the total current? How much of current does R2 take from the total current? So this is what we are seeking. How much is I1 and I2? So we can apply the current division principle, but forget about this principle for now, and let us know how these relations have been driven, right? So to do it, basically, let us simplify this electrical circuit. So the simplest form of the electrical circuit, we're gonna end up with R equivalent, and there should be like a source here with Vs. This is like the total voltage, and there should be a total current, which is I total, as given here, right? So how much is R equivalent? R equivalent here, it should be their multiplication R1 times R2 divided by their sum R1 plus R2. Why? Because they are parallel. Very simple. So if I ask you to apply Kirchhoff voltage law, apply Kirchhoff voltage law to this overall electrical circuit, So the voltage Kirchhoff law states that the Vs, it should equal to the I total or times the R equivalent. Agree? Then keep this relation on a side, like relation equation star. Make sense? Then if I ask you how much is I1, now let us calculate I1. So simply, as we mentioned, that any two, as we mentioned before, any two parallel resistances, they should have the same volt. That the volt over R1, it should equal to the volt over R2, it should equal to the volt over the source, which it should be Vs. The source here, it is a current source, yes, but it has a voltage as well, right? But how much is the voltage? It is Vs, this is the total volt that we just calculated here using this equation. Make sense? So simply, what does it mean? It means that the Vs, it should equal to the volt over R1 plus the volt, which it should equal to the volt over R2. Make sense? So if I ask you, and now let us calculate I1. If I ask you, or let us write, so we do have Vs equals. How much is VR1, the volt over R1? It should be the current over it, which is I1, and we have no clue how much is R1, and this is what we are seeking, times R1. And how much is the volt over R2? It should be I2 times R2. Make sense? How much is Vs? Vs, we got it using this relation as the I total times R equivalent, which should equal to I1 R1, which should equal to the I2 R2. Make sense? So simply, if you decided to find I1 how much it is, simply what you're gonna do, you just gonna use these two relations together to solve for I1. Then if you decided to solve for I2, you're gonna use this one with this one to solve for I2. Make sense? So let us solve for I1 only for now. Let us find I1. So simply I1, it's gonna be I total times R equivalent divided by R1. Agree? How much is R equivalent? We got it by R1 times R2 divided by R1 plus R2. So simply, if let us consider I total, it is a common factor here. So we're gonna have here like the R1 times R2 divided by R1 plus R2. There should be R equivalent, and this should be multiplied times R1, and the overall it should be multiplied times I total. Agree? So simply, is it fine if we remove R1, cancel R1 with R1? Yes. So what we're gonna end up with, we're gonna end up with R2 divided by R1 plus R2 times I total. So we're gonna end up with this relation, which is this one, right? So if we decided to read this relation very simply, so if I ask you how much is the current over R1, so you're gonna tell me it should be the other resistance, which is R2, divided by the sum of the two resistors. Multiply it times the total current of the electrical circuit. And this is what defines this is the statement of the current division principle. The current division principle states that in case that we do have only two resistances, this expression just for only two resistances, okay? In case that we do have only two resistances which are in parallel, the fraction of the total current flowing in a resistance in one of these two resistances is the ratio of the other resistance to the sum of the two resistances. So again, which is very simple, if I ask you how much is I1, you're gonna tell me it should be R2, the other resistance, divided by the sum of the two resistance, which are the R1 plus R2 times the total current. This is gonna give us the I1. How much is I2? It should be the R1 divided by the R1 plus R2 times the total current, the sum of these two resistances. Make sense? This is the current division principle and the voltage division principle. Now, since we have discussed these two principles, the voltage division principle and the current division principle, along with our discussion and the example that we consider for calculating the equivalent resistance, let us use these two principles along with the equivalent resistances to do analysis for different resistive circuits. And let us consider some examples here, starting with example 1. For this example 1, the original electrical circuit that is given is this one, with R1, R2, R3, and this is the total source, which is a voltage source of voltage of 90 volt. So the procedure and the steps basically that we start, I'm gonna write down these steps here. So step 1, so in step 1 basically, your objective is just to distribute the current through the electrical circuit. Make sense? Very simple, like what we did million times before. So simply what we're gonna do, let us distribute the current, start with the total current, which is IS, where S stands for the source. And we do have here this total current is gonna keep going. It means that the current over R1, it should be the IS. Then at node 1, this current is gonna be split and divided into two currents as I1, and there should be I2. So if I ask you how much is the current over R3, you should know that it is I2, and the current over R2 should be I1. Make sense? So given this configuration basically, and this distribution, you're gonna move to the next step, which is step 2. And in step 2, your objective is just step 2, just calculate. Remember that here we will not apply Kirchhoff voltage law or Kirchhoff current law or Ohm's law. This is another method that we discussed before. Here we would like to calculate the equivalent resistance. So the step 2, we're gonna use the equivalent resistance. Step 2, it means that calculate the equivalent resistance of this electrical circuit. Make sense? So if we calculated the equivalent resistance here, as we did before, simply R2 and R3, both of them are parallel resistances. Agree? Why? The current has been split over them. So what does it mean? It means that I'm going to combine these two into R equivalent 1. This R equivalent 1, it should be their multiplication, R2 times R3 divided by their sum, which is R2 plus R3. Agree? R2 is given by 30 times 60 divided by 30 plus 60, which is gonna, if you did the calculation, we're gonna end up with 20 ohms, which is gonna give us R equivalent 1. Then if after these calculations, we're gonna end up with a simplification into this form of the electrical circuit, into this form as R1, and we combine R2 and R3 into R equivalent 1. If we distributed the current again after every simplification, you have to calculate to distribute the current again. Distribute the current through the electrical circuit, so it's gonna be IS, and the current here is gonna be still IS, the total current. So what does it mean? It means that these two resistors, they do have the same current over them, which is IS. It means that R1 and R equivalent 1, they are series resistors. So what does it mean? It means that we can combine both of them into an equivalent resistance, which is gonna be their sum. If you sum 10 plus 20, this is gonna give us the 30. So what does it mean? In the second step, we just calculated the R equivalent. We just got it by 30 ohms. And this is gonna be the second step. As for the third step, your objective is just to calculate or apply Kirchhoff voltage. Find here is just to find either the current or the voltage, because this is the simplified form of the electrical circuit. It has three components. There are three things here. There should be here the current, right? There should be the current IS, which should be IS as well here, right? The same current, the one that rotates within this electrical circuit. So we do have three things: VS, IS, R equivalent. R equivalent, we already have its value at 30 ohms, and the VS is already given by 90 ohm and 90 volts. So the only unknown is the IS. So step 3 is just to calculate the unknown within these three parameters, which is IS in this case. So what I'm gonna do in step 3, what I'm gonna do here, just calculate, find or calculate the total current of this electrical circuit. So the total current IS, if we applied Kirchhoff voltage law, it should be VS equals IS times R equivalent. We said that this is for any simplified circuit is going to be this relation. So automatically IS, we're going to end up that IS, it should be the VS divided by R equivalent. VS, which is 90 volt, divided by the 30 ohms, which is R equivalent that we just calculated above. So we're going to end up with 3 amperes as the current source. This is the total current, and this is going to be the third step. Make sense? Then these 3 steps are fixed for any given electrical circuit, and as long as we are doing analysis for resistive circuits using the equivalent resistance method. So these 3 steps are fixed. Anyway, you're going to do it. Do this or apply these 3 steps. Then you can read what is required and see what are the requirements for this electrical circuit. Let us assume that it is required for this electrical circuit to check whatever the overall power that it is conserved for this electrical circuit as we did before. What does it mean? It means that we have to calculate the power over R1, the power over R2, the power over R3. To calculate the power over all of these different resistors, we have to find the current over each one of them. We don't have the total current, which is IS. We already got it for R1. It means that we knew or we do have a value for the current over R1, which is IS, which we just got it by 3 amperes. But how much is the current over R2, R3? We have no clue. We have to find it. We can find this one by applying Kirchhoff current law and Kirchhoff voltage law, but we don't need to apply these ones through this method. Through this method, we can use either the current division principle or the voltage division principle. Now our main concern is to come up with a value for I1 and I2. So what does it mean? It means that we have to apply the current division principle over the 2 resistors, which are R2 and R3. And these 2 resistors, they are parallel resistors. As we mentioned before, that the current division principle can be applied. It is only applicable to parallel resistors, and they should be 2 resistors according to the equation that we mentioned above. According to this equation here, the current over a branch over one of the resistances, it should be the resistance of the other resistor divided by their sum of the resistances times the total current which has been divided over them. So again, so for example, if I decided to calculate I1 and I2, what I'm going to do here, so step 4, just for this problem, what I'm going to do, I'm going to apply the current, division principle. According to the current division principle, what does it mean? It means that I do have here, according to this electrical circuit, I do have the total current, which is IS. It has been divided into I1 and I2 over R3 and over R2 and R3. So what does it mean? It means that if we decided just to draw this one, so we're gonna have the IS, which at this node has been divided over 2 resistances. Here we do have R2 and we do have here R3, and it has been divided into 2 currents, one as I1 and I2. So what does it mean? I do have IS has been divided into I1 and I2. Let us just use uppercase. So how much is I1? So I1, it should be the resistance of the other resistors, or the other resistance. So the I1, this is the current over R2. So it should be R3, the other resistance, divided by the sum of R2 plus R3 times the IS, which is the total current. This is the total current that has been divided, split it. So if I decided, and how much it should be I2 according to the current division law, so it's going to be the R2, the other resistance, divided by R2 plus R3. This should be multiplied times IS. So these are the two equations that we're going to use them. So if we did it basically, and let us do the calculations here. So how much is IS? We just calculated IS, the total current, by 3. And R2 and R3, they were given by 30 and 60. R2 is 30, R3 is 60. So R3 is going to be 60. This is 60. This is 30. And this is 60. And this is 30. This is 30. This is 60. Right? And this is the 3 ampere. So if we did the calculations, we're going to end up here that the I1 is going to be 2 ampere and the I2 is going to be 1 equals 1 ampere. So we got the current over these two resistors, R2 and R3. Then simply we can calculate the power, the electrical power over all of these different electrical elements. So we can calculate the power over the voltage source, calculate the power over R1, the power over R2, and the power over R3. And even if we sum all of this power, it should be, their sum should be 0, as we discussed before. Now let us move to another example here of this electrical circuit, that we do have this source of a volt, Vs is already given by 12 volt. And we do have a resistance of 12 ohms, 25 ohms, 35 and 10 ohms, 6 ohms. And it is required for this electrical circuit. Let's see what is the requirement for this one. And let us, for example, find the voltage V1. It is required to find V1 and V2. So it is required to calculate how much is the voltage over the 30 ohms and the voltage over the 5 ohms. So the requirement for this example, it is required to find V1 and V2. Forget about the requirement, the solution procedure is the same. The first step is just distribute the current through the electrical circuit. So we're gonna start from the source as usual, which is voltage source. So we're gonna have here IS, this is the total current, which is gonna be over the 12 ohm will be the IS as well. At node 1, this current is gonna be divided into two currents. So we're gonna have here, let's say I1, then we're gonna have here I2, agree? Then at node 2, the I2 current will be divided further, will be divided more into I3 and I4. Then this I4 is going to keep going here into I4 as well. Then everything will be collected back again here at this node till, so I1 with I2 and its division will be collected back here. So what should be the current over the 6 ohms? It should be the total current which should be received back again to the electrical circuit. Make sense? We have to start from the resistance at the end, away from the source, which is the Vs. Make sense? So if I ask you what is the relation between the 5 ohms and the 25 ohm, they are in series. Why in series? Because they do have the same current. Agree? So simply, so step 1 is just to distribute the current through the electrical circuit, and we did that. Second step, or step 2, is just to calculate the overall equivalent resistance for the electrical circuit. So step 2, calculate R equivalent, which is the equivalent resistance of the circuit. To calculate R equivalent, basically what I'm gonna do, let us divide it into like some simplify this electrical circuit. So what we're gonna do here, these two resistors, they are in series. Agree? Why? They do have the same current. So these two are series. So we can combine both of them into R equivalent 1. R equivalent 1 is going to be 30 ohms. Make sense? Just sum. And their equivalent will be parallel to the 30. Why parallel? Simply again, try to get rid of these two resistances. So what is the relation between this resistance and this one? The current has been divided, the total current, which is I2, has been divided over them. It means that this one, it should be parallel to this one, or their equivalent, the equivalent of these two, it should be parallel to the 30 ohms. Make sense? So what does it mean? It means that we can combine these three into another R equivalent 2. R equivalent 2. Where if we did the calculations here, we did the calculation for R equivalent 1, we got it by the 25 plus the 5 ohms, which give us the 30 ohms. This is for R equivalent 1. For R equivalent 2, it should be between parallel, which should be the 30, which is this, the sum of these two, times another 30, which is this 30 ohms, because it is parallel, divided by their sum, which is 30 plus 30. If we did the calculations, this is going to give us R equivalent 2 will be 15 ohms, Make sense? So now we combined all of these three resistances into just one. So what does it mean? It means that we can get rid of two, we just can use only one. But this one equivalent, the resistance, it should be 15 ohms, not 30. So anyway, if you ask yourself, what is the relation between this resistance and this one? These two are parallel. Why parallel? The current, which is the total current IS, has been split or divided over them into I1 and I2. So what does it mean? It means that the R equivalent, the equivalent of all of these three resistors, which is R equivalent to, which is 15, it should be in parallel to the 10 ohms. Make sense? It means that is fine to combine these, all of these, into another R equivalent. It's going to be R equivalent 3. So we're going to combine all of them into a third R equivalent, which is going to be R equivalent 3, which it should be as two parallel resistances. One is the 15 times the 10 ohms divided by the 15 plus the 10 ohms. This is going to give us the, if we did the calculation, this is going to give us 6 ohms. Make sense? So now we end up with the R3. Now we can get rid of all of these resistances, all of these, and just use only one resistance, which is 6 ohms, the R equivalent 3. What is the relation between this resistance to the other two resistances here? You're going to find that the current passing over, because we canceled all of these three resistances, right? We canceled these two, three. We're just going to end up with one resistance here in this position. This resistance will be in series with the other three, with the 12 and the 6. So what does it mean? It means that is fine to combine all of these resistances of the electrical circuit, and this is going to give us the overall R equivalent. This is going to give us the overall R equivalent. R equivalent is going to be the sum of the R equivalent 3, which is 6, plus the sum of the 12 and the 6 ohms, because all of these resistors have been combined into one resistance, which is with 6 ohm. 6 ohm, which is this one, R equivalent 3, will be in series with the 12 and the other 6 ohms. So 6 ohms with another 6 ohm and 12, if you sum, this is going to give us 24 ohms. This is going to give us the overall R equivalent, the equivalent resistance for this electrical circuit, and this is going to be the second step. The third step, as you remember, we agreed that these three steps are fixed, are the same for any electrical circuit. So now we simplified this electrical circuit into this simplest form as follows. Like we're going to have here R equivalent, and we're going to have here only one source, which is Vs, and there is a current over this electrical circuit as Is. So simply, what is given, what is unknown? R equivalent, we got it by 24 ohms. Vs is given by 12 volt. It means that the unknown is Is. So the objective for the third step is just to calculate the unknown, which is the source current or the overall current, which is Is, as we just give it a name as Is. So how much is Is? If we apply Kirchhoff voltage law to this electrical circuit, it states that Vs equals Is times R equivalent. So what does it mean? It means that Is, it should be the Vs divided by the R equivalent. How much is the Vs? It is already given by 12 voltage up there. So it's going to be the 12 divided by the 25 ohms, which is the R equivalent here, which means that we do have 0.5 ampere as the total current, which is going to be half. Make sense? So this is for the three steps, the first three steps that are fixed for any electrical circuit using analysis of any resistive circuit using the equivalent resistance method. Now the objective is just to find value for V1 and V2. What is V1 and V2? V1, this should be the voltage over the 30 and the voltage over the voltage over the 30 and the voltage V2, this should be the voltage over the 5 ohms. So to calculate V1 and V2, basically, we need I3 and I4. Why? Because if I ask you how much is V1, you're going to tell me that V1 it should equal to the I3 times 30. Agree? How much is V2? It should equal to the I4 times 5. Make sense? So what does it mean? It means that I should find I3 and I should find I4. To find I3 and I4, basically you should find first I2. Anyway, it means to find I2, intuitively you're going to find I1. So it means that you're going to find that we have to calculate all the rest of the currents, which are unknown within this electrical circuit, to figure out how much is V1 and V2. So it means that we should find I1, I2, I3, and I4. Make sense? But remember, don't use Kirchhoff voltage law, Kirchhoff current law. Make sense? So how we can find these unknown currents? Since you are seeking values for currents, you have to apply the current division principle. And the current division principle, it is applicable to two currents. Between two parallel resistances. So you're going to ask yourself, starting for example for I1 and I2. Starting for I1 and I2. So if we decided to rewrite again or redraw again this electrical circuit, just to explain this point here, we have combined all of these resistances, these three resistances. If you just go over this green circuit into R equivalent 2, right? We combine this 3 into R equivalent 2. So if we redraw this electrical circuit again, and this is going to be the fourth step, just apply. Just apply the current division principle. So for this electrical circuit, if we decided to redraw this one very quick, or basically, okay, let us draw it just to explain it to you. So we do have here one resistance, and there should be one resistance here, then another one, and should be the 6 ohms, and this should be the source Vs. Agree? And this should be this resistance. Here it is 12.6 and there is 10. This should be the 10, this is the 12 ohms, and this should be the 6 ohms. This should be the R equivalent 2. Why the R equivalent 2? Because we combined all of these three resistances into just one, which it should be R equivalent 2, that we just calculated by 15 ohms. So if we decided here to distribute the current, we already have here the total current, which is Is, which it should be split into I1 and I2. So if we decided to apply, it means that we do have the Is will be divided into I1 and I2. So let us apply the current division principle to these three currents. So we're gonna say that the I1, it should be the resistance of the other resistors. I1, this is it goes over the 10, so I'm gonna take the other resistance, which is the 15 ohms, as we calculated above. So it's gonna be the other resistance, which is 15, divided by the sum of these two resistances, which is 10 plus 15, times the total current, which is IS, which we just got it by half. Make sense? So it means that this should be multiplied times 0.5. If we did the calculation, we're gonna end up with 0.3 ampere. This is for I1. Agree? But how about I2? I2, this should be the current over the R equivalent 2. So it's gonna be the other resistance, which is 10, divided by the sum of the two resistances, which is 10 plus 15, times the original or the overall current, which is 0.5. If you did the calculation, we're gonna end up with 0.2. And as you can see, the sum of these two currents, it should equal to 0.5. Why? Because if you decided to apply Kirchhoff current law, the sum of these two resistances, it should be the same. Agree? So this is gonna give us the I2. So we got I1 and I2. Let us do the same, but for I3 and I4. Make sense? I3 and I3, I4, these are the division of I2. So what does it mean? It means that here, if we apply it again, but this time we're gonna apply it for the I2, it should be divided, it has been divided into I3 and I4. And remember that how much is the resistance that I4 goes over? It goes over the 30 ohms. Make sense? According to the electrical circuit, it goes over the 30 ohms. But how much is the resistance that I4 goes over? I4 is gonna go over the 5 plus the 25 plus the 5, right? Because we combine these two. Remember that the current division, it should be applied between only two resistances. So the I3 goes over the 30, this is one resistance, but the I4 goes over two resistances, which is 25 and 5. It means that I have to combine them into R equivalent 1, which we just calculated before as 30. So it means that the resistance over I4 is 30 as well. It is 30. So intuitively, if you're gonna find that, if you just look at it, we do have here 30 ohms and 30 ohms for the I3 and I4. So even without doing any calculation, I3 is going to take half, I4 is going to take half of the I2. Make sense? I2, which is already we calculated before as 0.2 ampere. But let us apply the Kirchhoff, the current division principle to I3. So I3 should be the other resistance, which is 30 of the I4, divided by the sum of the resistances with the 30 times the total current, which is I2, which we just got it by 0.2. If you did the calculation, this is going to give us 0.1 ampere for the I3. The same, if you did the same for I4, is going to be also 30 divided by 30 times 0.2, which is going to give us also 0.1 ampere. And this makes sense since these two currents are going to feed the same resistances. Make sense? So this is for the step 4, is just to apply the Kirchhoff, the current division principle, and we calculated all the currents that we already have in the total current I1, I2, I3, I4. Now, how much is V1 and V2? V1 is going to be I3 times 30, is going to be I4 times 5. This is for V2. So simply, it's just to calculate the step 5. This is just calculate the unknown or the requirement, which is our V1 and V2. So V1, it should be the I3 times 30. I3, we got it by 0.1 times 30, which is gonna give us the 3 voltage. And how much is V2? Simply, V2 is gonna be the I4 times 5. So it's gonna be the I4, which is, we got it also by 0.1 times 5, which is gonna be 0.5 voltage. So these are for V1 and V2. and these are the requirements for this example. Let us consider another example here, example 3 for this electrical circuit, and it is required, this is the requirement, is just to find V, this is the volt over the source, how much it is, but this source, it is a current source of, gives 8 amperes, and how much is I, the current over this resistance of 10 ohms. So to find this, let us apply the procedure. The step 1 is just distribute the current over the electrical circuit. So if we decided to distribute the current, we're gonna have here, this is the total current, which is, we knew it is 8 ampere. Let us give it a name for now like EIS, but you should understand that this IS is already given by 8 ampere. This IS will go over the 5 ohms, then at node 1, it's gonna be divided into 2 currents here. So we're gonna have here like I1, and there should be I2. Then at node 2, I2 is going to be split or divided into 3 currents as I3 and I4. And there is I5, I'm sorry, 4 currents, I5. And there should be a 4th one as I6. Make sense? So the I2 at node 2 will be split over 1, 2, 3, 4 currents, as shown here, I3, I4, R5, and I6. And this I6 is gonna keep going. So it means that this I, it should be the I6 that I'm considering according to my distribution. And the current over this 10 ohms, it should be the same current over this 10 ohms. So if we decided to calculate, and this should be the step 2, is to calculate R equivalent, the equivalent resistance. Step 2, calculate R equivalent, the equivalent resistance for this electrical circuit. To calculate R equivalent, we're gonna divide it into multiple R's, right? So we're gonna have here, first of all, we're gonna combine these 2 resistances, the 10 ohms with the 10 ohms, into one equivalent resistance. Agree? As R equivalent 1, where these 2 are series. Why series? They do have the same current. So we're gonna have here R equivalent 1, R equivalent 1, it should be 20 ohms, the sum of the 10 plus 10. Make sense? Then if you're gonna look that, if we cancel one of these 2 resistances like this 10, what is the relation of this 10 ohms? So we cancel this one. So what is the relation of this resistance to this resistance to this resistance to this resistance? These 4 resistances, they are parallel. Why? The total current has been divided over all of them. Again, if you reset back again or remember the definition of parallel series, that the current, it should be divided over them. In the previous examples, we considered the cases that the current has been split between 2 resistors or over 2 resistances. But it would be divided over 3 or 4 or 5 or 10 resistances, it depends, right? Here it has been split or divided over 4 resistances. So how we can calculate their equivalent? Their equivalent is gonna be using the inverse law. Make sense? So what I'm gonna do here, we already combined these 2 into an equivalent one. So if we decided to calculate the equivalent here, so simply what I'm gonna do, I'm gonna combine all of these resistances, all of them, into another R equivalent. It's gonna be R equivalent 2. So the R equivalent 2, it should be the equivalent of all of these resistances together. So how much is R equivalent 2? R equivalent 2 is gonna be calculated using this equation as 1 over R equivalent 2. It should equal to the inverse of the R equivalent 1 that we just calculated by 20, plus, because these 2 has been combined into R equivalent 1, which is 20, and plus the inverse of the other 20 ohms, which is this one, plus the inverse of this 20 ohm, plus the inverse of this 20 ohm, and remember that there should be 20 as well. If we did the calculations here, so we're going to end up with only one unknown, which is R equivalent 2. So how much it is? If we did the calculations for this electrical circuit, okay, So it's gonna be 1 over 20 times 4, right? So it's gonna be 5. So this is gonna give us 5 ohms. So what we've done so far, we combined all of these resistances, all of them together into R equivalent 2 with 5 ohms. Then if we cancel this one, cancel this one, cancel this one, cancel this one, cancel all of these resistances, except only one with 5 ohms, what is the relation of this resistance to I2, or the 20 and the 25? If you're gonna see here, if we combine all of these, you're gonna find that the total current passing over this 5 ohm, the equivalent one will be I2. So what does it mean? It means that 20 ohms with the equivalent of this resistance should be series. Why? They do have the same current. So what does it mean? It means that it means that is fine to combine. We can calculate a third R equivalent. R equivalent number 3 is gonna combine all of these resistances, including the 20. So we're gonna have R equivalent 3. So R equivalent 3, in this case, R equivalent 3 is gonna be the 20 plus the R equivalent 2, which we just got it by 5. So this is gonna be 25 ohms. Make sense? Then how about if we cancel all the resistances except this one, for example? So this one to the 25, it's gonna be better. Why? The total current, which is IS, which is 8 ohms, it should be split or divided over the I1 and I2, which is gonna be the current over the equivalent, which is R equivalent 3 and the 25 ohms. Make sense? So what does it mean? It means that we do have the current, which is gonna be divided, which is into I1 and I2. So what does it mean? The R equivalent 3, which is the equivalent of all of this resistance, should be better to the 25. So we're gonna end up here with R equivalent 4. It's gonna be the equivalent between R equivalent 3 times the 25 divided by the R equivalent 3 plus the 25. Why the multiplication over division? Because they are better. These two they're gonna be better. So we're gonna have here like R equivalent 4. Like we combining all of these together into R equivalent 4. Make sense? Then the R equivalent for itself, it means that we're gonna cancel all the resistances except this one. This one to this one, it is series because they do have the same current at the end. Make sense? So what does it mean? It means that I'm gonna end up with an overall R equivalent. So this one, if we did the calculations, let us do the calculation for this one. R equivalent 3, we got it by 25. This is 25 and this is 25 as well. So it's gonna be equals the 12 it's gonna be half, 12.5 ohms. Then simply we can calculate the overall R equivalent. This is gonna be the R equivalent, the overall R equivalent, which is gonna be the R equivalent 4, plus the 5. So it's gonna be the 5 ohms plus the R equivalent 4, which is gonna be the 17.5 ohms. Make sense? This is for the step 2. Step 3, remember that the first 3 steps are fixed. It's just to calculate the unknown. Remember that now we simplify this electrical circuit into this simple one. But the source here, it is a current source of 8 ampere. Remember that the source, there is a current source of 8 ampere. So the unknown is going to be the V. V here stands for Vs, which is the total voltage. And this is one of the requirements of this problem. So how much is V? Simply, so it is required to find V, the total volt, where R equivalent that we just got it by 17.5 ohms. So simply, if we apply, so it means that calculate the source voltage. It is the unknown. The current is already known. Where the current here, which is IS, that we just, it is already given by 8 ampere. So Vs, according to Kirchhoff, which is V here in this problem, it should be the Is times R equivalent. So V is going to be the Is, it is 8 ampere times R equivalent, which is 17.5. This is going to give us times 8. This is going to give us 140 volt. And this is one of the requirements. If this is the only requirement we've done of this problem, but there is one more requirement, which is the current over this 10 ohm. This current, it is I6. So to find I6, basically, we have to apply the current division principle, right? We have to apply the current division principle. But it is a little bit tricky here, but because the current division principle, we can apply it over only 2 resistances. But here we do have 4 resistances. So what does it mean? It means that first of all, we have to find I2. We have to find I2 first. Because this I2 is the one that is going to be splitted or it's going to be divided. Make sense? So how we can find I2? I2, it is the division of the total Is into I1 and I2. So let us calculate I2 first. So what I'm going to do here, step 4, apply current division principle. I do have the total current, which is Is. Let us use a different color. So I do have the total current, which is is going to be divided into I1 and I2. And then we're going to ask ourselves, so the total current, which is is going to be divided into I1 and I2. So how much is the resistance over I1 and I2? I1 is going to feed only one resistance, which is the 25 ohms. Okay? But I2 is going to feed all of these resistances. So what is the equivalent of all of these resistances? We calculated as R equivalent 3. As you can see, this is R equivalent 3 that combine all of these resistances, all of them together. So what does it mean? It means that I1, it will feed the 25 ohms, will feed only 25 ohms, but this is going to feed the R equivalent 3, which we just calculated above here by the 25 ohms. We calculate by 25 ohms. So also it's going to feed 25 ohms. So since the two resistances are the same, so directly we're going to say that I1, it should equal to the I2 according to the current division principle, as we mentioned in the previous examples, is going to be half. Each one, it will be half the total current, which is 8 over 2, which is going to give 4 amperes. So we got I1 and I2. And basically we are interested in just I2. Make sense? So we found I2. Now I2 is going to be divided or split over 4 resistances. The first resistance is the 20, the second one is the 20, the third one is the 20, and the equivalent as well is going to be 20. As you can see, this 2 will be combined into 20. Make sense? So intuitively, you do have a total current, which is 4 ampere, is going to be split and divided, and it should be divided equally. It should be divided equally over 4 resistances. You got my point? Equally over 4 resistances. And instead of just 2, it's going to be divided equally over 4 resistances. So intuitively, it means that each one of these resistances is going to take the quarter of the total, because it has been split over 4 equal resistances. So from this, just for this problem, just for this special problem, we're going to say that we do have the total current, which is I2, is going to be divided into I3, I4, I5, and I6. Okay? We already have here I3 is already 20 ohms, I4 it is 20 ohms, IS it is 20 ohms, but I6 this is R equivalent one, which is also 20 ohms. So intuitively that we're gonna find that I3 it should equal to the I4, it should equal to the I5, it should equal to the I6. Very similar, it is typically the same, like in case that you have only two resistances in this case. So equals the 1, 2, but it should be divided over 4 resistances, which is gonna give us 1 ampere to each one. So now we got I6. I6 it should be the current I, which is the requirement. It is required to find the current I. So intuitively or finally we're gonna say that the I, and this is the final requirement, that the I it should equal to 1 ampere, and this is gonna be the second requirement, and that's it for this problem. Now let us move to example 5. I've skipped example 4 because it is very similar. You can try this one at home, no worries. And let us move now to example 5. Example 5, we do have this electrical circuit with 4 resistances, and we do have this current source of 3 amperes. So, and it is required for some reason, let us see what is the requirement for this problem. It is required to find V, which is the volt over the source, and I1 and I2. It is required to find I1, how much it is, how much is I2, and Vs. So these are the requirements, Vs, I1, and I2. Make sense? So stick to the procedure. The first 3 steps are the same, are typically the same. Step 1 is just to distribute the current starting from the source. So we have the total current here as Is. This Is is going to be divided at node 1. This is going to be node 1 into, which is already, Is is already given by 3 ampere, by the way. And it's going to be divided here into I1 and I2. And this I2 is going to keep going as I2 as it is over the 5 ohms. Make sense? Then this I1 and I2 both will be collected back again at this node, and you're going to reset back again into the total current as Is. It means that the current over the 6 ohm, this resistance, will be the Is, which will reset back again to the source. So this is how the current is distributed through this electrical circuit. And this is for step 1, and just to distribute the current. Step 2, if you remember, is just to calculate the R equivalent. For the equivalent resistance for this problem, as you can see, I2 go over the same current, goes over the 25 and the 5 ohms. It means that the 25 and the 5 ohms, both of them can be combined into an equivalent resistance as follows. So we're going to have here R equivalent 1, which combine these two together as R equivalent 1. And this R equivalent 1, it should equal to 30 ohms, their sum, because they are series. Then if we cancel one, and we consider just one, this 25, which should be the 30, will be parallel to the 20 ohms, to this resistance. Why? The current Is will be split or divided over them. It means that we can combine these 3, all of them together, into another R equivalent, which is going to be R equivalent 2, but this R equivalent 2 is going to be the sum, the calculation of the R equivalent 1 times the 20 divided by the 20 plus the R equivalent 1. Why? Because they are parallel. The current has been split over them. So if we R equivalent 1 is already given by 30 times 20 divided by the 50, this is going to give us 12 ohms. Agree? Then now we combine all of these resistance. So simply we can get rid of 2 and just use 1. This one, the current over it will be just Is, the total current, which it should be the same current over the 6 ohms. It means that this R equivalent 2 with the 6 ohms, it should be series. And if we combine them, we're going to end up with the simplest form of this electrical circuit. So what does it mean? It means that we can conclude, and this is going to be for step 2, that the overall R equivalent for this electrical circuit is going to be the sum of the 6 plus the R equivalent 2, because they're going to be series, which is going to give us the 12 plus 6, which will be 18 ohms. So this is for step 2. We just find the R equivalent. Make sense? What next is just to find either the current or the volt. It depends on the unknown. Now we simplified this electrical circuit into this simplest form. We do have R equivalent with 18 ohms, and we do have a source. But now in this case the source is just with 3 ampere. This should be the IS. It is a current source, and there should be Vs here, which Vs, this is the unknown voltage. This is one of the requirements. So according to Kirchhoff voltage law to this electrical circuit, we're going to say that the Vs equals the Is times R equivalent. So what does it mean? It means that the Is, which is already 3 ampere, times the R equivalent, which is 18. If we did the calculation, we're going to end up with 3 times the 18. This is going to give us 54 volt. This is for the Vs, and this is one of the requirements, by the way. Then what next is just to find I1 and I2. To find I1 and I2, we have to apply the current division principle, right? Very similar to what we've done before. So the current applying the current division principle, we're going to end up with that. We do have Is. This is the total current, which it should be divided into I1 and I2. So if you ask yourself, what is the resistance that I1 goes over? It goes over only 20. This is the only resistance that I1 goes over it. Just 20. So we do have I1. It has resistance of 20, or it feeds 20 ohms. But how about I2? I2 is going to feed 2 resistances, not just one. And these 2 have been combined together into R equivalent 1, which we just got it by 30 ohms. It means that it feeds 30 ohms. Make sense? So if we did the calculation and we applied the current division principle, we're going to say that I1, which it should be I1 as written in the problem, it should equal to the other resistance. I1, it feeds 20, so I'm going to take the other resistance, which is 30. So it's going to take the 30 divided by the sum of the 2 resistances, which it should be the 20 plus 30. So again, the I1 feeds the 20. I'm going to take the other resistance divided by their sum, times the total resistance that feed them, the overall resistance, which is Is. Is is given here by 3 ampere. This is the total source current, which is 3 ampere. So it's going to be 3. If we did the calculations, we're going to end up with 30 over 50 times 3. So this is going to give us 1.8 ampere. How about I2? I2 is going to be the same. It's going to be the 30. It's going to be the other resistance, which it should be the 20, divided by 20 plus 30. This should be multiplied times the overall resistance, which is 3. So this is going to give us the 1.2 ampere. And as you can see, the sum of these 2 resistances, according to the Kirchhoff current law, it should equal to the total current, which is 3 ampere. Make sense? And that's it for this example. The last example that we're going to consider today is this example 6. That we do have 1, 2, 3, 4, 5 resistances and one current source of 5 ampere. And it seems that it is required to calculate V and I2 and I1. So let us calculate let us consider that the requirement here, it is required. These are the requirements just to calculate V, which is the volt over the source, and I1, and I2, where I1, this is the current over the 10 ohms, and I2 is the current over the 9 ohms. So the solution procedure is going to be the same. The first three steps are typically the same. It's just to distribute the current through the electrical circuit. So we're going to start from the source as IS. This is the source current, which is already given by 5 ampere. At node 1, this source, this is going to be node 1. This source is going to be split or divided into like for example, because here there is I1 and I2, so I'm going to use like, for example, I3, and it's going to be divided into I2, which is typically the same like I2, where I2 is going to go over the 9, then it will be collected with the I3, which is going to go over the 18 at this node to recede back again into the IS. So what does it mean? It means that the total current will be collected back again at this node, and it means that the current over the 6 ohms will be IS, which is 5 ampere. Then at this node, this current IS will be divided at node 2 into two currents, into like, for example, I4, because we already used I1, I2, I3, so, and I1, right, where this current, it should be the I1 here. Make sense? And then the I4 with the I1, both will be collected back again at this node to recede back again into the IS. So this is how the current goes through this electrical circuit. So from this distribution of the current, basically, we realize that the 9 and the 18 ohms or resistances, they are parallel, while the total current has been divided over them. So what we're going to do, we're going to combine these two into an equivalent resistance as R equivalent 1, R equivalent 1. How much is R equivalent 1? R equivalent 1, these are two parallel, so it's going to be their multiplication divided by their sum, which is 18 plus 9. This is going to give us the 9 times 18 divided by the 18 plus 9, which is going to give us 6 ohms. 6 ohms. This is for R equivalent 1. How about R equivalent 2? Remember that this is step 2. Step 1 is just to distribute the current. Step 2 is just to calculate the equivalent resistance. Now we combine these two together into one resistance. So simply we can get rid of 1 and just consider like 1 with 6 ohms resistance. So this one, what will be the current over this equivalent resistance will be the total IS, which is going to be the same as the total IS here. So what does it mean? It means that this equivalent with the 6 will be series. This equivalent with the 6 will be series. But before that, basically, because the IS itself will be split into I1 and I2 over the 10 and the 40. So what does it mean? It means that it is better to combine these two first. So if we decided to combine the 10 with the 40, both are parallel. Why parallel? Because the current has been divided over them. So this is going to give us R equivalent 2. So I'm going to consider the second R equivalent as the 10 times 40 divided by 10 plus 40, which is going to give us 400 divided by 50 as 8 ohms. So if we have a look to this electrical circuit, we're going to have only one resistance over this side, one resistance over this side, and one resistance in the middle, and all of these three resistances will be series because the total current as IS will gonna keep rooming. It means that this electrical circuit is gonna look like this one. This is gonna be R equivalent 1, and we're gonna have here on the left R equivalent 2, and there is something in the middle here as the 6 ohms, and this is gonna be the total current as 5 ampere, and and the same current is gonna keep rooming in this electrical circuit. So all of them are series. So we're gonna end up with the overall resistance R equivalent as the sum of R equivalent 1 plus the R equivalent 2 plus the 6 ohms. We got this one as 6 plus 8 plus 6. So if we sum all of these together, this is going to give us 20 ohms. And the overall resistance, this is going to be step 2. Step 3 is just to find one of the unknown. Now we end up with this very simple electrical circuit. We do have a source, this is a current source, and we do have an equivalent resistance here in this way. Just R equivalent of 20 ohms. 20 ohms, this is the R equivalent. And there should be here V, this is the volt over this source, and it has a current of 5 ampere. And it is required to calculate this volt. This is one of the requirements. So if we applied Kirchhoff voltage law to this electrical circuit, we're going to end up that V equals IS, which is the total current, IS, times R equivalent, which is going to give us the IS as 5 ampere as given, times 20. This is going to give us 100 volt. Make sense? This is for the first requirement, but how about I1 and I2? Again, I1 and I2, these are the divisions of the total current. IS is going to be split into I3 and I2. So I2, if you decided to calculate it, or I1 the same, we have to apply the current division principle. Make sense? The current division principle states that for any two parallel resistances like the 8 and the 9, the current over I2, it depends on the resistances of these two, or I3. So basically IS without IS has been split into I2 and I3. So as we usually do, we do have the IS, it will be divided into I3 and I2. How much is the resistance over the I3? 18, but I2 it has just 9, so it's going to be 18 ohms, but this one has 9 ohms. So simply we just interested in I2, so I2 is going to be the other resistance, which is 18 divided by their sum, which is 9 plus 18 times the total current, which is IS, which is already the 5 ampere as given above. It was already given here by 5 ampere, the total IS. So what does it mean? It means that we're going to have 18 divided by the 9 plus 18. This is going to give us the 0.67 ampere. I'm sorry, times 5. It should be multiplied times 5. So this is going to give us the 3.34 ampere. This is for I2. How about I1? I1 also is the division of the total current IS, which is 5 ampere, but it is divided between the 10 and the 40. So what does it mean? It means that it divided between I1 and I4. So what does it mean? It means that we already have here IS, which has been divided into I1 and I4. How much is the current over I1? It is 10, and over I4 it is 40 ohms as given above. Agree? So what does it mean? It means that the I1, the current I1, it should be the other resistance, which is 40, divided by their sum, which is 40 plus 10, times the total current, which is 5. So this is going to give us 40 divided by 50 times 5. This is going to give us 4 ampere. And these are the requirements, I1 and I2, in addition to the total voltage as 100 volt. Make sense? So that's it for today, for this lecture. The other examples, you can go over them at home. If you have any question, just, send me or ask. Don't hesitate to ask it through the regular office hour meetings or by sending email.